Hey everyone, so welcome to this deep learning course, episode number 2. So in that part, we'll be talk about that deep neural network actually. So the deep neural networks actually add hidden layers to your network and uncover the complex relationships. So that is how. So in that video, we'll be talking about actually. So in this lesson, we are going to see that how we can build neural networks and are capable of learning the complex kind of relationship deep neural nets are famous for actually. The key idea here is modularity and building a complex neural network from simpler functional units actually. We have seen how linear unit and computation and linear function. Now we will be see how to combine modify this single unit to model more complex relationships actually. So let's deep dive into that. So the neural networks typically organize their neurons into layers actually. So when we collect together linear units have common set of input, we get a dense layer actually. So let me explain that. So you will get and some understand actually. So so in that part, I have an inputs and dense and output. So in that part, so I have an x0 and x1 and a 1. So in that part, I have a two neurons actually. So in that, I can create two neurons. So in that neurons, so first x0 will call the first neuron. So this the multiple neurons we can organize, right? So that is called a dense layer actually. So the x0 and we'll calling that two layers actually, and so this one calling that both neurons and so this one calling that same. So the multiple inputs which we are calling that multiple neurons at the same time, the neurons will generate that output actually. So that is called y of 0 and y of 1 actually. So in that a dense layer, two linear units receiving that two inputs and a bias. You could think each layer in a neural network as a performing same kind of relatively simple transformation. Through a deep stack of layers, a neural network can transform its inputs in more and more complex ways actually. So more and more complex ways. In a well trained neural network, each layer is a transformation getting us a little bit closer to a solution actually. So this is how that dense layer will it get works actually. And the next part will be talk about that activation function actually. The activation function, it turns out, however, that two dense layers with nothing in between are no better than single dense layer by itself. Dense layer by themselves can never move us to out of the world lines or planes. What we need is something non-linear. So what we need are activation functions actually. So without activation functions, neural networks can only learn linear relationship. In order to fit curves, we'll need to use activation functions on that actually. An activation function simply some functions can we apply each layer's outputs, its activations. Most common is a rectifier function is max 0 comma 1. That means So max 0 comma x actually, and the rectifier function has graph that lines with the negative part actually. So in that this is the negative and this is the positive actually. So the rectifier function has a graph that's line with a negative part rectified to 0. So this is the 0 part actually. Let me draw it. Yeah. Applying the function to an output of neuron will be put bend in the data, moving away as from the simple lines. When we attach the rectifier to a linear unit, we get a rectified linear unit actually. So that is called as a ReLU, rectifier linear unit. For this reason, it's common to call the rectifier function the ReLU function. Applying the ReLU activation to a linear unit means output becomes a max 0 and at the same time w into x plus bias. So which we might draw a line in a diagram like, so we'll get it right. So in the diagram like, so x and also I have a bias, so I can just call that rectifier linear unit actually. So rectifier linear unit like that, same that actually. So this is the, oops, sorry, my bad. So this is the rectifier linear unit actually, and so in that it will be giving that y actually. So you're saying you get it what I'm saying, right? So it will be applying that fitting the non-relationship, and it's a around work around of neurons actually. So the next part will be looking that stacking the dense layers actually. So don't skip that. We'll go the topic. Now that we have some non-linearity, let's see how we can stack the layers to get complex data transformation actually. So let me put some example over there so that you will get an understand over there. So in that part, I can wrote it up x of 0 and x of 1 and 1. So it called bias. So in that, I can create some ReLU rectifier linear unit actually. So in that part, so I can just wrote that ReLU. So in that part, I can just make a circle over there, and also I can put another neuron. So in that part, so in that part I can put, so this is called hidden layers actually. So in that I can create that another thing, and also I can put it for bias, and this one also have an bias, and finally I can connect all the ReLU rectifier linear unit with a single neuron, and that neuron will return that output actually. So this one will be connect with that, and this one will be connect, and this one, and the same as this one. So this is how it will be gonna work. So at the same time, these hidden layers will communicating with each thing actually, and all the things will be communicating with that actually. So this bias will communicating with all the layers, and this is how it will be getting work actually. So this layer we called as a hidden layer. This is also same as hidden layer, and this is the linear actually. So that stack of dense layers makes a fully connected network actually. The layers before the output layer and sometimes called as hidden layer, since we never see the outputs directly actually, but it will be get processed, but we can't get that output from the hidden layers actually. Now notice the final output layer is a linear unit, actually meaning no activation functions. That makes a network appropriate to a regression task where we trying to predict some arbitrary numeric value. Other task like classification might require an activation function on the output actually. The next thing we can more and more important thing, we can building a sequential model using Python. So let's go with that. So the sequential model we have been using will connect together a list of layers in order from first to last, right? So the first layer gets an input, and the last layer produces the output. This creates the model. I'll show that actually. So already we created a one dense layers, right, that stacking the dense layers. So in that we have here two inputs along with the one bias. We have a four relo hidden layer, and then again three relo hidden layer and one linear layer actually. So like that we just created. So same as in that Python, I can just create some simple thing actually. So let me open that code block, and so let me open that tensorflow. So in that, okay, so once I can just import the TensorFlow from Keras, and from layers also I just include that. So in that, as per the our architectural design, so we have a uh, two input x0 x1 and four hidden layers for the relu, and again three hidden layers activation of relu, and one linear layer actually. So that same as I'm going to I'm going to type a code based on that actually. So in that code block, so I can model equal to keras dot sequential. So in that I'm going to create an array. So inside that array, so the first thing, we have a four hidden layers, right? So I can put, so layers dense. So in that dense layer, I have an four units actually. That means the four layers actually. So the four relo activation actually. So in that I can put activation. So let me expand it. Relu. And also, so the how many inputs we are going to get in that actually. So I can get input yes such. shape. Okay, so in that I'm getting the two inputs actually. So this is how that layer gonna will work actually. Okay, so the next thing, we designed that one shape actually, that one four relief activation layers actually. The next thing, three layers actually, that we need to design it. And so I can put comma, and oops, sorry, yeah, can put comma, and again layers dot dense. So in the dense, we have here, as per the diagram, we have here just three units actually. And so in that activation relu, and we don't have the input shape for that, because uh, this is that second layer, units 3, right? So this second layer will get the output from the previous layers actually. So I can just close it. And the finally we need to create a linear layer actually. So in that part, just we can put dense, and in that units equal to 1. So it will be the linear output layer we generated actually. So be sure, pass all the layers together in a list, like layer comma layer comma layer comma layer, and so on, instead of as a separate arguments to an activation function to a layer. Just give it a name to the activation argument actually. So if you put the activation argument, so automatically it will consider, say, okay, this is a hidden layer. And so that hidden first layer should be a 4, and the second layer should be a 3, and the dense layer should be a 1. So this is how it gonna to be a work actually. So hope you guys you really like that video from this course. And let's see on that next chapter actually. So hope you guys you really like that video, and please subscribe my channel for more videos like this in the future. And thank you all. See you. Bye. We hope you found this video informative and helpful. If you did, please hit the like button and consider to subscribe our channel for more videos like this in the future. Also, don't forget to share this video with your friends and colleagues who might find it useful. If you have any questions or comments, please leave them in the comment section below, and we'll be happy to respond. Thank you for watching. We'll see you on the next video.